Today, we're going to go through a lot of stuff, and we're going to try to do it in a fairly short period of time. The first question I have for you is this. Is it possible, if you had a big enough rocket with enough fuel, to leave?
Yes.
To leave and not come back?
Yes. Didn't they do that?
and not come back?
And not come back?
Didn't they do that with
With
the Hubble?
the Hubble?
I'm an idiot. Okay, I'll leave.
You mean, I don't know,
What's the one?
just launch the Hubble and just say, yeah, we don't want it
There's the
anymore.
one-
There's one that just passed Saturn, though,
There's the
isn't
one
there?
that satellite. There's the one satellite that they have that.
Actually, there aren't any satellites that we have.
It's a telescope.
Because by definition, a satellite
Oh.
is something that comes back. What do you call a thing that you eject and it just goes on forever and never comes back? It's not called a rock.
A rocket.
Like that.
No, most rockets, almost every single rocket we've ever used has actually come back to Earth.
Really?
Yeah.
Well, are there any that hasn't come back
Exploration
here?
vehicle.
What do you call the thing that you launch with the expectation that it will never return to our solar
A
influence?
shuttle. Death Star.
Starts with a P.
Projectile.
It's called a probe.
Ah, dang it.
It's called a probe. And we have two probes. Two probes right now that are really, really, really far. Do you guys, anyone know what they're called?
Deep
It's not. That's not.
They're called Voyager 1 and Voyager 2. And one of them, I can't remember if it's 1 or 2, one of them's further out than the other one.
Voyager 1 is farther out, but
I don't remember because it all depends on what we had them look at on their way out and how much time they spent dilly-dallying in the solar system. Right?
Just put them out there.
So, and how much of a slingshot effect, so which one ended up going faster when we were done. Because we sent them in different directions.
Oh, really?
Yeah. So, Voyager 1 and Voyager 2, one of them we think we're still getting telemetry from. It's been out there since, 1979 maybe? Yeah, it's been going for a while, but just passed outside of our solar influence. So is now beyond that space where the gas from the sun is, and now it's getting into space where gas from other stars are.
with the delay from that, like, you know, it's like transmitting. With the delay for that be?
That's a good
The delay, yeah, the delay for that signal is like, is it 13 hours or is that, am I wrong on that? It's really long.
Good.
The speed of radio
13 hours isn't that
How
long if
fast?
it's not even in our solar system, is it?
Yeah, it takes a while. It might be days, I don't remember. It's a while. Okay, so it's 8 minutes for light to go from Earth to the sun.
Wait, what kind of waves? What kind of waves do they use to transmit?
Radio. They just need to have a radio on board. And the radio is solar powered, but at this point the sun looks like any other star to that satellite. So it's basically getting starlight and it's running off of starlight.
That's awesome.
Yeah. It's a starlight and nuclear.
That's cool.
Didn't we
Yeah,
like,
I think nuclear. I think it's got a little thing that decays every once in a while and produces a little bit of heat.
So what happens if it reaches a planet?
What are the chances that if you go in any particular direction that you crash into something?
Well, eventually.
It's like a
Minuscule. Minuscule.
Well, would you ever be, if you launch anything in any direction, would you eventually be affected by the gravity of another star?
Absolutely. And that's the goal. That's the goal. All right, so here we go. So what does it take to launch something fast enough such that it just goes forever and never comes back? What would you have to do?
You have to reach a certain velocity.
You have to reach something called escape velocity. Now here's the key. Escape velocity, I have a difficulty thinking about how to calculate escape velocity. Here's the way I think about it instead. I just showed you a graph of total energy. And what did you find for total energy for circular orbits? Your total energy is always what? Negative. How come? Because the potential energy is always bigger than the kinetic energy. Is it possible, if you don't do a circular orbit, instead you do a different shape, is it possible to have enough energy such that your total energy is no longer negative? Could you do it?
Yes.
What would you need to have? How big would your kinetic energy need to be?
It would have to be
Not double anything. It would need to be,
just greater than.
it'd have to be bigger than your potential energy is negative, because your potential energy is always negative, right? You have to have a kinetic energy that is greater than the amount of negative potential energy you have. Now here's the kicker. The closer you are to the sun or to the planet or to Earth or whatever, the more negative potential energy you have, right? So what do you need?
Just get farther away from the
You need to be going faster. The closer you are to the planet, the faster your launch velocity needs to be. Alright? So theoretically, if you could go to Mount Everest and launch from there, that would be a pretty good spot to launch from. Right? Or actually the best spot to launch from, of course, is the equator, because then you get the whole spinning of Earth's, the fact that you're actually moving at over 1,000 miles an hour already just because the Earth is spinning around. Right? Do you ever think about that?
Is that why it's in like Florida or whatever? It's so close to the equator?
Yeah, we would rather launch from Cape Canaveral than from, say, Maine. Right? Because you get that extra little bit of go because you're already spinning. You're already moving.
Not to mention it's nice with Cape Canaveral.
Yeah,
Yeah.
right. Weather can be a little better in the winter.
Yeah.
All right.
It's actually 17 hours, 17.6 hours.
17.6 hours is the delay. Nice.
That's not even that
And which
bad.
Voyager is it?
Voyager 1.
Yeah.
Voyager 1. Okay. Voyager 1 is further
It
out.
says that the velocity, not the velocity, distance from Earth changes during certain times of year because.
Right, because it goes like this.
Yeah.
Yeah. So, yeah, 17 hours to receive a signal from Voyager 1.
But they said they'll keep transmitting till 2025 is the predicted time.
Yeah.
Before everything decays.
Yeah.
Generators decay.
Nice.
Which is actually pretty cool.
Yeah, I don't think, I said it runs off a solar panel. I don't think its solar is doing anything at this point. I think there's just not enough light out there for it to generate enough photons to.
It says it carries a gold-plated recording disc.
Yes.
With information from Earth.
Yes.
Just in case intelligent life ever finds it.
Yes. They took it. I remember actually. I don't remember when they launched it because I was too young, but I remember hearing about it a few years later, and they recorded everything that they thought was important on a gold disc, on an actual disc of gold. Why gold, by the way? You guys know?
Doesn't corrode.
It doesn't corrode, right? It's just gonna stay.
Big
Right. So anyway, let's move on. So escape velocity. In order to do that, you have to have kinetic energy that's bigger than your potential energy is negative. So your total energy is greater than zero. So at a certain initial kinetic energy, the rocket will have enough speed to go forever. This speed is called escape velocity. Here's how to figure it out. What is the requirement in order to escape again? Kinetic has to be greater than potential. In other words, the 1/2 mv squared has to be bigger than the GMM over R. Agree? Which means that the v squared has to be bigger than 2 GMM. Wait. Oh, GM over R, because one of the m's canceled. Which means that the velocity has to be greater than square root of 2 GM over R. Oh my gosh, that's their square root of something GM over R again. So how does escape velocity compare to the velocity for a circular orbit? What was the velocity for a circular orbit again? square root of GM over R. What's escape velocity? Square root of 2 GM over R. So what's the relationship between those two speeds?
Times
Square root of 2. So here's the kicker. If you had a satellite that's in a circular orbit going around Earth, and you multiplied its speed by 1.414, what would happen to that satellite? It would just go boom and never come back.
Awesome.
Well,
Yeah.
that's not much. If it
Well, you have to,
backtracks
you do
another-
work to slow it down. So it came back. Yeah.
It's not like much faster.
It's not much, it doesn't seem like much faster, but think about
How
this.
fast it's moving.
How much fuel does it take to get the thing into orbit to begin with? A lot.
But
So now you're gonna take,
doesn't it encounter a lot of resistance from the atmosphere?
you're gonna take twice as much fuel. Right? Say that again?
Doesn't it encounter a lot of resistance in our atmosphere?
You mean a satellite? How much drag is there on a satellite? How much drag is there on a geosynchronous satellite, do you think? You remember how far out a geosynchronous one is?
35,000 kilometers.
It's like if the planet's this big, then a geosynchronous satellite, if the planet's 8,000 miles in diameter, and this thing is 22,000 miles out,
That's juicy.
how much air drag is there?
No, not as
None.
much. Not as much. there,
None.
But I'm saying
None. None out at geosynchronous. There's no air out at geosynchronous. Our little band of air is very, very thin. However, there is significant amount of air if you are on a low Earth orbit, like one of those spy satellite things. Spy satellites, they like to have as close to Earth as possible so they can take as good of pictures as possible. Right? Or mapping satellites or whatever that you want to have close to Earth so they get good pictures. Yeah. Good?
Are those ones constantly expending fuel to like?
Yes, they constantly have to give themselves a little boost to overcome the energy they're losing from hitting air molecules all the time.
Are they start them like crashing back to Earth?
They don't, because eventually they run out of fuel and crash back to Earth.
Yes, because they like.
Right. That's how you get rid of a low Earth orbit satellite, is you just let it crash.
But
So what
don't they
happened-
plan that out pretty well? It's like it's gonna crash into like the ocean. Or
No, they plan it out so they are pretty sure that it will hit the Earth, and that's about it.
something. Okay.
Do they plan out?
Let's hope it doesn't land in North Korea.
Yeah.
Yeah, no, the chance of a satellite actually hitting something important
Wow.
is very low. But it is there, and every few months you get a report that such and such so and so satellite is going to be crashing down sometime in the next 6 hours. We have absolutely no idea where it's going to hit, but there's a 70% chance that it's going to land in the ocean.
Okay.
The Northern Lights is
What's that?
The Northern Lights is
Yeah.
Good.
The northern what?
Northern Lights. That is another effect. Let's talk about Northern Lights here in 2 weeks when we talk about electrostatics. Sound good? All right. Actually, no. We're going to talk about it when we talk about magnetism, but bring that up again. And hopefully there will still be Northern Lights to see. All right, so here we go. So we've got escape velocity. Oh, hey. Side note. Let's say you had a dog floating in space with a little helmet so it could breathe.
Just the helmet.
And you had a flea on that dog, and fleas we know are invincible. What would the escape velocity for the flea be to leave the dog? Really big speed or really small speed? Wait, isn't the flea attracted to the dog?
I guess.
Yes. But it's a very low gravity.
GM over.
It'd be square root of 2 GMM over R, or it's 2 GM over R, but, let's see, what would this velocity be? It'd be square root
What's the radius?
of 2 times G. How big is G, do you guys remember? 6.67 times 10 to the negative 11. Mass of the dog, which is, I don't know, how big is a dog?
100 pounds.
100 pounds,
Oh,
50,
that's the big dog.
20 kilograms for a dog. So 20 divided by the radius of the dog. I don't know, maybe this much, like 10 centimeters.
For our discussion.
So 0.1. So it'd be 20 divided by 0.1 times 6.67 times 10 to the negative. So how big's that velocity?
Really small.
Really small. So could a flea escape a dog?
Yes.
Yes, in space. Yes.
For objects that aren't circular, say you had an ellipse, not ellipse, how do you say it?
Are you? It's still always the distance from the center of the thing that you're trying to leave.
So
So here it's easier to leave than here.
So you had to find the center of mass of the dog,
Right.
and then the distance.
And it depends. It's easier for the flea to leave the nose of the dog than the backside of the dog.
Okay.
Yeah. All right. So, okay, let's do another thing. It's where we're going to do a little. This is a true story.
Ask once on the test, but it will kick your butt back.
Yeah.
Thank you.
Once upon a time, young Lieutenant Bruce had the privilege of launching a satellite into space. And what I want you to do is don't look at the right answer. I'm going to put something up on the board, and then I'm going to pause the video, and I want you guys to answer the question. All right, so I'm going to go ahead and pause the video now. If you fired the thrusters such that the satellite gets pushed and loses speed, it's going to take a new elliptical path that's going to intersect with the Earth and crash and die. So that's bad. All right? What if you fired the thrusters such that the satellite gets pushed toward Earth?
That's a bad idea.
Would you increase or decrease your speed?
Neither.
Neither. All you would do is change the angle that it's traveling at. So you'd actually get a new ellipse that maybe looks something like, change the angle here, so, something like that, right? Which would be counterproductive, and it would probably crash into the planet, right? Because
Yeah.
the whole idea of the low Earth orbit is just barely high enough to not crash into the planet. And if you make this circle elliptical, it's got to be smushed in one direction, and then you're screwed. It's going to go up higher on the ends, but it's going to be smushed in the middle. Okay, so if you fired the thrusters such that that it gets pushed away from the planet, guess what happens?
Oh, larger.
It would shift the ellipse around, and you'd still crash into the planet. So what's the end goal?
Indoor.
No, you're already in orbit.
Oh, it's into a lift.
To get into an orbit that requires more energy. So in order to get more energy, what way do you have to fire the thrusters? You have to fire them in the direction that you're traveling, and when you do that, you end up with an orbit that looks like this.
Have you ever played Kerbal Space Program, Mr. Bruce?
Who?
Kerbal Space Program.
Never. All right, let's move
You
on.
would love it.
Okay.
You'd love it.
Yes, but we do have, oh my gosh, we are so far behind. All right, so that's interesting. So to get, this is called, by the way, this is called the transfer orbit. Transfer.
Then when you get out to point B,
So now you're in this elliptical transfer orbit, and you're going wrong, wrong, wrong. When you get out to point B, what way do you fire the thrusters?
in the direction of your velocity.
Against.
Why? 'Cause
When you get
have to
right here,
circulate
you're
it.
traveling this way, right?
I'm sorry, the other way.
What way do you want to push the satellite?
Down.
Do you want to push the satellite in the direction it's going, or away from the direction it's
Away from
going?
the direction that's going.
So what would happen to your energy if you pushed away from the direction you're going?
Kinetic energy would decrease.
You would lose energy, wouldn't you agree, if you pushed the satellite this way? So what would happen when you got here?
You fall
Start
down.
falling down.
And you'd crash into the planet again.
So you want to go forward.
So which orbit takes more energy, the transfer orbit or the final orbit?
Trans. Wait, now I'm in
Final
it.
order.
The final orbit, how come?
Yeah, I just realized
Because
that.
the radius is greater.
The radius is greater means you're farther from the Earth, which means you got more potential energy, and the potential energy we know for a circular orbit is more important. So you need to add energy at B, and the only way to add energy at B is to fire the thrusters again in the direction you're going. So, when you're putting a satellite into a geosynchronous orbit, you start from a low Earth orbit, you fire the thrusters once at point A to speed yourself up so you get more energy to get to the transfer orbit, and then you fire the thrusters again at B in the direction you're going to round out that orbit, add energy. Yeah.
How does it go into a, like, because every single other time you fire thrusters, it goes into an elliptical orbit, how does it go into a circular?
What's the difference between an ellipse and a circle?
Okay.
Well, one is the locus of point from one point.
How do you circularify this transfer orbit?
With the thrust line.
You have to give yourself enough speed. How much
Like grow
speed
up.
do you need?
Let's get
Square root of G.
You need exactly square root of GM over R. But you're not coming into it with that much speed, right? Because you're here, you sped up, but by the time you got out here, you slowed down again. So you need to speed up again to get square root of GM over R in order to get that big circle again. And this square root of GM over R is different than this square root of GM over R. How come? Because R at A is smaller than R at B. Does that make sense?
Yes.
All right.
So if you wanted to just come back and spend more, would you just not do anything once you got to that
It's
point?
literally
So like if you're going from A and then it got to B and then you just wanted to come back, you just wouldn't do anything.
Yeah. If you're in that transfer orbit, at A you fired your thrusters. And this is, by the way, if something goes wrong, when you're setting up, you're trying to get your satellite on orbit, you only have 2 spots that you can pick from in order to thrust such that you'll get this path. You can either thrust here or you can thrust here. If you miss your opportunity and the thrust doesn't happen at point B, guess what you got to do? You got to wait till it goes around again, and then when it gets back to B, you fire your thrusters at the next opportunity.
Wow, that'd be a waste of.
It's a waste of time. All right, but it does happen. Stuff goes wrong. Your systems fail. You know, stuff's not. Maybe the solar panels aren't aligned correctly. I don't know. There's a million things that could go wrong. All right.
But I have a question. Wouldn't you not be able to gain velocity instantaneously, so you have to start your burn before point B?
Yeah. So how long a burn are we talking about? We're talking about, typically, you're not going to have multiple hour-long burns. You're going to have short burns with big thrusters in order to make this work. All right. So we're going to save the last one till tomorrow.